Hi, welcome to our webinar for plastics part design. My name is Amee Meghani. I'm a mechanical engineer from the University of Texas at Austin. I specialized in product development and have had 10 years of industry experience, 4 of those in injection molding plastics. Arvind is a manufacturing engineer with a specialty in additive manufacturing, and he's our simulation specialist here at GoEngineer. We are presenting from the Dallas office. So let's get started. For this webinar, the expected audience is for the beginner to moderate range. We have some good tech tips and design recommendations. So we hope it will be beneficial to the moderate user as well. So Arvind, can you please get us started with an introduction of kind of the general injection molding process?
Sure, Amee. So injection molding is a mass manufacturing process. The way it works is the machine that you see on the right bottom, you have a hopper and pellets that you put in, and there is a barrel and a screw that heats up those pellets through the heating elements and friction. The pellets become molten plastic, which is then injected into the mold. Once your part is injected into it, the part then cools down after occupying all the space inside and solidifies, and it is then ejected out to drop outside. This is the injection molding process. Some quick comments about it. Because of the way it is set up, the mold has a high upfront cost. Usually takes a little bit to make it. But once you do that, the process of creating parts, the cost per part is relatively low. And that's what is very attractive about injection molding for mass manufacturing. It has excellent reproducibility and surface finish. But there are a lot of parameters that affect the plastic part design. That is what we are going to be talking about today. Some of the tricks to improve your design, your typical development process, an initial concept that you have. You can create a detailed product design where the dimensional specs and how it's going to look. You then do some validation to ensure where you're going to use the part, whether it'll be structurally valid for that application. And one thing that people often overlook when they're initially designing is design for manufacturing. So Amee, tell us a little bit about this part. We initially start with the detailed product design.
So what's particular about plastic part design is that you have this expectation that you designed something and you're like, okay, this is exactly what I'm going to get. But this is what happens. And a lot of that can be due to lack of knowledge or experience. And there's a lot of things that go into plastic part design, a lot of variables. And if you do some 3D printing and you do some other things to a point in your design cycle and 3D printing proves out form, fit, and function, there's still some pieces that 3D printing won't be able to predict. 3D printing can't predict the manufacturing flaws like warpage and shrinkage and things like that. So we're going to talk about some of those today and how we can avoid those manufacturing flaws.
Yeah, from an injection molding standpoint, there are so many things that affect how a final part looks like. The fill time, the manufacturing pressure of the machine, material composition, gate location, thermal expansion coefficient, viscosity of the material. All of these play a big part in the plastic's final part design. From a mold perspective, you have other things like packing time, cooling lines, pressure settings. So there's a lot that goes into it. Injection molding, while it has a lot of benefits, it is important to understand the process that governs how it works.
So from a managerial perspective, it should be known that a typical mechanical engineering curriculum doesn't necessarily have a plastics course. or plastics track, a lot of people don't know that. A lot of people assume that you're the technical resource and you probably already know all about plastic part design, and that's not the case. So I just kind of pulled up several curriculums, just from top engineering schools, and you'll see that there's no plastics track here. But there are other ways to increase your knowledge on this topic. You can network with other engineers. If you have communication with other tool makers, that can help. A lot of times if your tool maker is local, you can talk to them and really learn a lot from them. You can learn a lot by looking at flawed plastic parts and trying to understand why something happened that way, understanding the defects, why is this a short shot? And so we'll talk about some of this terminology. But we just, as engineers from an academic perspective, we really just learn kind of the microscopic, like, material science aspect of plastics. It's not something we learn academically, so it's something that we have to learn either from an advanced program or through experience.
Yeah, another consideration to keep in mind when manufacturing plastics is, from a managerial perspective, is the fact that 80% of the molds and the subsequent injection molded parts are actually made internationally. This is good in the sense that it reduces the costs of tools and labors, but there's a couple of things to keep in mind when you do this. One of them is communication. A lot of people have different languages. If you plan to visit the actual manufacturing facility, it might be a 20-hour flight, time differences and jet lag that you need to account for. Also, some of the countries have blackout days where there's power outages. They have different festive schedules. Just some of those things that you don't initially think about. So these are some of the things you want to consider when you are thinking whether to manufacture domestically or in a different country.
So when we talk about injection molding, there are two major topics. There's the mold design, so that's like the cavity design, and then there's also the part design. And today we're going to focus mainly on the part design. But a lot of the choices we're making here are affecting mold design. So we'll talk about where, one affects the other, but it's important to know that relationship. So now let's go on into some of our design fundamentals. Rule number 1 is that you want a uniform wall thickness. That's kind of the general rule, and the reason is that you want the molten material to flow evenly through the cavity. So, Arvind, can you show us this in the analysis software? What are we compromising? What is the trade-off if we don't have a consistent wall thickness?
Absolutely. So let's go ahead and switch to SOLIDWORks, where we have a model of a very simple plastics part design. And if you look through the cross section, you will see the constant thickness that you have. In this case, we have done a very simple injection molding analysis where we specify the gate location. And once we run this, we are going to notice how it fills. We see the molten plastic going from that initial gate location to the extremities of the design. One more thing to keep in mind is the pressure at the end of fill. For this specific design, the maximum pressure needed is 350 psi. But for the same part, I'm going to switch to a different configuration where we have a multi-wall thickness design. Let's look at the cross section and you will notice the difference in the thickness. So just for that thickness change, you could have looked at it from a structural perspective and think you are saving material. But from a plastics manufacturing perspective, you notice that now when you look at the pressure at the end of fill, you will have gone about 3 times higher in terms of the pressure needed. A lot of times there is a defect called short shots that we will talk about as well. So with the amount of pressure needed, you would need a bigger machine because the current machine doesn't achieve that pressure you need to fill the mold. So that's another thing to keep in mind.
So I wouldn't have thought that a small change like that would affect the pressure threefold. That was interesting to see. So the next tool is adding drafts or taper. If you're not familiar with that term, drafts are like, basically I have this image of a cupcake because it's kind of clearly explaining what's happening. If you're baking a cupcake, the side walls are drafted or tapered. And the reason this is done is because the cupcake, once the cupcake is baked and then cooled after baking, you remove it from the mold. But without that taper, you're going to have a hard time removing it and you'll just have kind of cake on the sides. So the draft allows you to remove the part from the mold easily. So even though draft itself doesn't affect the part, it does affect your cycle time. So you want to produce multiple parts in a cycle, and there are different cycle times depending on the size of your part. So draft is important as well, and some people specify, like some tool makers specify that they want a minimum of 3 degrees. It really varies from tool maker and what part and material you're using.
Yeah, and to add to what Amee is saying, when we saw that initial animation of the mold, to ensure the two molds separate, we want to add a good draft. Another functional reason is the same pressure that we just spoke about in rule number 1. I want to quickly bring up another example where the same model with and without draft, and even in this case with the same setup, same material, same gate location, we're going to notice that the pressure required has gone up about 20% from the previous example. It's not as bad as the multi-wall thickness case, but it has still gone up by not adding draft. So the idea of having the molten plastic flow through different regions of the model is very important as you consider draft angle in your plastics part design.
Excellent. So rule number 3, mounting bosses should be about 60% of the thickness. And I say that, but it's not like an exact science. But bosses and features inside your part that are similar should not be as thick as your global wall thickness. You want to have it a little smaller or a little thinner because you want to reduce sink marks on the opposing side of the part. So this image shows how when you have the same thickness on ribs, you can create some defects on the other side. You can also create some cosmetic flaws, if you don't monitor that thickness on some smaller features. So it really depends on the final application of that part, but you definitely don't want to compromise the integrity of that part. Your analysis tool can tell you if it needs to be 60% or 65%. You can actually run the analysis and get that sweet spot of what that thickness needs to be for those inner features. And the same thing applies for ridges. Ridges are often structural features, but if you don't choose the right thickness, you can get sink marks from them as well. You might have seen a plastic piece with just some vertical or horizontal lines from the ribs underneath, and that's because the rib thickness is not quite right, and upon cooling, you get those kind of linear indentations that are very, very minimal but enough to see. So Arvind, can you show us like a structural rigidity example, like a part with ribs? Can you show us something like that and what it looks like in the software?
Absolutely. Let's go back and switch to SOLIDWORKS. This time we will look at the structural aspects of our design. We will go ahead and open up the structural simulation tool. So in this case, we have a simple box, and let's look at an example of the stiffness through the frequency analysis that we can perform. I'm going to look at the first mode of vibration, which in this case, given the fixture points, is 450 Hertz, which is the first natural frequency. If I look at the second one, it is 523 Hertz. The same thing, if I go ahead and add a couple of ribs on the underside, I'm going to go ahead and add 3 ribs on each side, something very small, so not adding too much weight to the structure. But now if I go ahead and look at the frequency, the first mode has increased about 10% to almost 500 Hertz. The second one has increased almost 15% to 600 Hertz. So making slight design changes with ribs following the design guidelines that Amee just spoke about can help improve the structural stiffness of your design significantly.
Okay, so we have another rule, which is to avoid undercuts. You can't always avoid undercuts, depends on the design demands, but there are a lot of creative ways to get around undercuts, and if you can avoid them, it just reduces the cost of your part significantly. So undercuts are basically features on the side of your part, and the side of your part is relative depending on where the parting line is. So that's just some plastics terminology there, but if you have a top and a bottom and a hole as shown in this illustration, what that means is when the part is molded and when you're injecting the molten material into this cavity, you now have to have a placeholder for that hole, that geometry, so that the material will flow around that shape. And for that to happen, you have to have some kind of side action or tooling. Basically, like in this case, it would be like a cylindrical boss, that sits there while the material's flowing around it. And so you now have like a whole other section of your tool, and then you have to remove that section and then separate the cavity to release the part. So not only is it more tooling, but it's a secondary step in order to release the part. So you're increasing the cycle time, increasing the cost of your mold. So if you can implement some creative ways to get around that, you can keep the cost of the mold and the tool relatively low. So it's important to avoid that. So Arvind, we spoke about some rules, things we really want to abide by when designing the part, but there are a lot of things we don't see when we're a first-time plastics part designer. There are a lot of things we don't even know about, and when we get the first part, we're like, wait, what is this? How did this happen? What are some of these manufacturing defects that I didn't think of right away?
Yeah, let's go ahead and look at a few more plastics injection molding terms, which that you may want to think about as you consider your designs. So once again, we're going to look at a thermostat casing that has been injection molded. We have the GoEngineer logo on one side now, and in this case, our injection location is there, and we are going to go ahead and run the animation for how this part fills up. You can see that the flow front coming in from the left and another one coming in from the right meet somewhere in the middle. That causes a well line to create, because when you have multiple flow fronts meet up, there is imperfections in the microscopic level when you have those two different flows. These are unavoidable for any plastics part, but you want to avoid them in structurally critical areas. So if you have a well line in a structurally critical area, look at moving the gate location so that the well line moves, or making some other small changes. Another thing unique to plastics injection molding is air traps. When we looked at the initial flow of how an injection machine mold is made, the gap between those molds before I inject any plastic has air in it. So where does that air go? That air needs to be vented out. And this is done through what's called venting lines. These venting lines should be placed in regions such that they are outside of the parts. You want the air traps to be on the outsides so that they can be vented. So if an air trap is on the middle, is on the inside in the middle, then it's very hard to have a venting line go there. So to make the manufacturing process a little easier, you want the air traps to be on the outside. Similar to that, sink marks is another one, where if you have an abrupt change in the thickness, because of the thermal profile that it creates and the longer time it needs to cool down, a sink mark is going to be generated in those regions, and you want to take that into account. Another place where you typically want to avoid structurally sensitive areas. We spoke briefly about short shots in the previous example. If the pressure in the injection molding machine is not enough, then short shots are developed, and you want to avoid these, so have adequate thickness for your parts. Over to you, Amee.
Okay, so we've spoken about design rules. We also talked about some weird curveballs that you can expect in the manufacturing process. So now let's talk about how you can improve your design. So injection molded parts often have alignment issues. And in this example on the left, you've got a lid and a box. And you can design, for perfect circumstance. But if you put a chamfer or a fillet for a good lead in it, it'll help you, actually make that closure for the lid to the box. There are alignment issues often with plastic parts. So, Arvind, can you tell us a little bit more about why we might see alignment issues?
Yeah, so that second diagram that you see in the bottom, you see the chamfer cut, and it gives you more room to sit in place. The additional room is because you want to account for warpage as one of the potential imperfections due to injection molding. So let's go in and look at what warpage is real quick. Warpage is the effect of temperature profile as your molten plastic cools down and solidifies. It's going to shrink, and you're going to see warpage effects due to uneven shrinkage. In this phase, now keep in mind that warpage in this part, I have magnified it about 5 times so that we can actually see it with the naked eye. But we can see that the warpage is relatively uniform, and that is helped by the location of the gate being central. As we are talking about this, the uniform shrinkage can be accounted for by having a slightly bigger mold. But let's look at another scenario where the warpage is not uniform. In this example of an impeller, we look at the warpage in this case, and you're going to notice that on one side it warps a little more than the other side, and that's going to have a direct impact on the performance of this part. Once again, this one is not magnified, and you see the one region is going to warp a little more than the other, and because of it, it directly affects the performance of the part. Just wanted to hit on a couple of things more. The one reason where 3D printing is useful is when you can test some of these issues beforehand. Also, something like SOLIDWORKS Plastics helps you export the warped shape itself so that you can test your designs on the warped shape, and you know if something will work or not based on the amount of warpage, and you can look at form, fit, and function of the warped shape itself.
Okay, so Arvind, you're saying that you can save the deformed shape that the software gives us, and we can save that as a 3D model and print that and then test it?
Absolutely. So you can run tests to look at the form, fit, and function with an STL 3D printed model before you create your first mold. And in some cases, you can also counteract the effects of warpage and ensure those are minimal enough in your design.
So before we go on, I just wanted to share a few more alignment examples, just a couple of solutions that I think are really good. The one on the left is a step with a little feature to keep those two pieces aligned, and I really like that. You can probably create a feature similar to this along the inner perimeter of some kind of enclosure. So from the outside, you wouldn't be able to see it, but it'll still help with alignment. A box like this on the right, you have holes in mounting bosses. You can slot one of the holes just a little bit to accommodate a little slop in there, and then that minor warpage won't be so obvious or evident to the naked eye. So this one I really like. This is 3 examples of assembly and alignment. So in the first one, you have a screw-on or a twist-on assembly, but they molded an arrow indicator. So that gives your end user some feedback on what the final position should be. The middle one gives your user auditory feedback when you snap something in place. And once you get past that stepped edge, then they understand that this item is locked in place. We have some built-in SOLIDWORKS design features on the mold tools command manager. It's called Snap Fit. Mounting bosses are also there. So these aren't features you have to design from scratch. You just have to enter a few parameters and SOLIDWORKS will kind of do the work for you. And then the third example builds upon the second one, where you have a snap groove that you snap it on. So that's kind of like your vertical or your Z direction feedback. But then you also have another feature to indicate the orientation to keep it from rotating around that boss once it's snapped shut. So next is, let's talk about orientation of components. Another thing we need to be a little more intentional about in our design decision is orientation. So sometimes you do want a part to be attached only in one possible way. You don't want to have any other possibilities, but sometimes you do want to give the end user multiple possibilities. You want it to be aligned in multiple ways. So you have to think about that from the assembly perspective and what it is you want for the end user, and then make that alignment decision on those parts. So labeling and instructions, this is something that I don't see a lot. So Arvind, if you turn over a plastic part, like anything, like a chair or something, what are some things that you see?
Stickers, some instructions, do's and don'ts. You might have an attached instruction sheet that comes with it as well, maybe?
Yeah. One of the things I see is kind of the recycling logo, and maybe I'll see the company who manufactured it. I know a lot of times I've turned something over to see, where did this come from? And I don't see that info at all. So I don't know where to get another one. So some people aren't even putting their names or brands on the product. But beyond that, you can give your end user a much better experience by integrating instructions or diagrams. So if you're doing like an electronic enclosure, you can emboss, kind of like your perfect path or the diagram for your wires, indicators, things like that. So all of that can be really useful to the end user or the one assembling it, the one buying it. So whether it's a consumer product or a component for someone who's assembling a product, you can speed up that process by adding that value, just molding in some instructions or indicators.
And just to add real quick, going back to one of the rules from before, you want to ensure you have fillets or chamfers in those regions. So there is an easy flow of the plastics to those intricate areas.
Okay, eliminating hardware. Why is this important? Hardware introduces a lot of labor costs. Labor costs significantly increase the cost of your part. While the tool is really expensive, labor cost is also a continuous repetitive expense, whereas tooling is a one-time cost. You also want to avoid all the other things that come with hardware. Like you've got to manage the hardware, you've got to add a Ziploc bag, instructions for the hardware. Managing all of that also is a cost. And the sky is the limit for the problems that exist with hardware in some instances, especially in kind of the consumer product environment. There's always an issue. Like I'm sure you can recall a time where you've opened a box and you just didn't have the hardware you needed to put it together. So that's kind of a wasted Saturday. So we can really end a lot of user frustration by integrating some smart fixtures. So Arvind, do you have an example on a feature to eliminate hardware? Like what can you show us in the software?
Sure. To highlight a little bit more about what you were saying, it is important that as we make our designs more simplistic for the end user, it just means more work for us at the back end to ensure the product is well designed. In terms of eliminating hardware, we look at a lot of snap fit features, and it is often used in plastic part design. So let's go ahead and look at an example here of a snap fit. This snap fit buckle example, we want to make sure that we have adequate force to push it down and go into the groove, but not too much force where is needed, where a consumer cannot push it down. And if it's too little, then there may be too many high stress areas and it might break off. So we want to make sure we create a good design taking all of these considerations into account. In this case, I have a simplified two-dimensional analysis, and let's go ahead and look at the stress results in animated. This will help us decipher how much stress to apply so that the buckle goes in and goes into place and comes out as well. Not only that, we can also see what is the amount of stresses that develop as you move the mechanism. So once again, as we go into a more detailed design, you want to take a lot of things into account to make sure you're making informed decisions on some of the design choices that you have.
Okay, so kind of like a buckle for a car seat. You want to be able to unbuckle it, but you don't want your child to unbuckle it.
Absolutely.
Okay, so we're kind of wrapping up here. Just a couple of final remarks. One thing that you do want to take into consideration is the appearance. Texture disguises some of these manufacturing byproducts, so to speak, like flow marks, parting lines, reflections. So texture kind of helps you in that way. And you need at least a minimal amount of texture. So once you cut the mold, and once you've decided that your part is exactly the way you want, you've done like your prototype, you've done your first part out of the mold, you've done some analysis and you're happy with that part, texture is a secondary operation. So what they do is they go into the cavity and they apply that texture so that when molten material flows in there, it comes out with that texture. So it's really important that your design is finalized, because any rework done to the mold, then you also have to retexture it. And that is an added cost and more time. So texture, it does help you, but a lot of people aren't making the decision on texture until later down the road. And that's a problem, because some really aggressive textures require more draft. And you have to cut the mold with like that degree of draft. But if your texture requires, a larger degree of draft, you might be in trouble. So you want to at least think about texture early on and kind of have a general decision on that.
Yeah, and one more thing to keep in mind with textures, some of those considerations are good. You could potentially have textures for ergonomic reasons as well. Let's say you want a good grip for the end user using it, things like that.
Yeah, good point. So another consideration is color. With neutral colors, like anything in the grayscale region, those are usually easier to match between batches. So let's say your first production run is 1,000 pieces, and then the demand goes up and you need to make 5,000 more pieces. Well, if you had wanted a special color, it's going to be hard to get that same exact color match, that same formula. It'll take some time to get there. Neutral colors are easier to match between batches. And it's also hard to get a rush order for specialty color sometimes. So that's another consideration.
Great. So, wrapping up, all in all, we spoke about best practices for plastics part design. We spoke about the injection molding process itself, making small changes to your design to make use of some of the benefits of injection molding. And we spoke about some design rules as well. I would like to thank you for your time today. This is Amee and Arvind from GoEngineer bringing you plastics part design. Thank you.